An important thing in mathematics, especially in multivariate calculus, is calculation of finding the mass and the moments, or the center of masses, the moments in the center of masses. The idea does stem from a lever arm. That if you have a balancing point on a lever arm and some mass some distance away from it, then an m2 times x2 has to equal m1 times x1. And finding this positional point, if we were to make this the origin, is finding the moment, or talking about the moments, which are related to the sum of the masses times their position argument. What we do then is extending this into 3 dimensions. What you want to do is you want to find the total mass of the body. And we can think of some 3-dimensional object consisting of little point masses all inside of it, an infinite amount of point masses of different radial distance from the center. And these point masses collectively, if we could sum them all up, then the mass, total mass of the body, would be the sum of all the little mass elements. Now, if these mass elements were even, we could look at these as being little cubic pieces of matter, and not just points. And these masses would have a density, some change in mass over all of them. And we could find then that we take the limit as n goes off into infinity, that the mass is going to be the sum of the density per unit of volume times the change in volume element. And so this becomes an integral. So the first part we need in calculating centers of mass are the total masses involved. The next part are the moments. And when we did 2-dimensional plates, we calculated the moment with respect to the x-axis or the y-axis. The first moment with respect to a plane is the triple integral of that region with the distance to the point. So, for example, if we look at, what plane do I want to look at here? The moment about the YZ plane. So the moment about the YZ plane will be the triple integral through the region of the distance from the x variable in the xy plane, from the origin, times its density function, times its volume element. And again, if we remember, back in Calc 2, we did the region for a two-dimensional object, and we did x times the density in xy times the change in area. And so there's a parallelism in the idea here in what we're looking for. This means we can get a collection of information about our object. And if we take the fact that to get the center of mass, we needed the moment in the y-axis and the total mass, what we can say is that the mass of the object is the triple integral through the region of the density function by the volume element. The first moments about the planes, for the YZ plane, is the triple integral times x times the density function times the differential of the region. About the xz plane, then, is the triple integral times y times the density function times the mass element. And then about the xy plane is the triple integral through the region, solid region, of z times the density function times the volume element. And this is telling us really how kind of where the lever arm is for each plane. And so to find the center of mass, you take the moment in the YZ plane divided by the total mass, and that'll give you the center along the x-axis. It'll give you the x value for the center of mass. The y value for the center of mass is the moment about the xz plane divided by the total mass. And the z value for the center of mass is the moment about the xy plane divided by the total mass. Again, if we look back at, I think it was chapter 8. So this is three-dimensional, solid, and its center of mass, and a two-dimensional plate, the mass was a region times its density function times the area element, and the density will just be a function of xy at this point. And then in the moment about the y-axis, which was the region integral x times the density function, the region about the moment about the x-axis, which is the region y times the density function integrated across the area. And the center of mass in the x direction was the moment about the y-axis divided by the total mass. And the center of mass y value was the moment about the x-axis and its center of mass. So the variables permutate across the spaces based on what you need. Let's look at finding a center of mass of a solid object. So let's get my solid object here. So we'll find the center of mass of constant density. So center of mass with a constant density bounded below by the disk z equals 4 minus x squared minus y squared. Oh, nope, that's above. Bounded below by the disk, x squared plus y squared is less than or equal to 4. So that's a circle of radius 4 about the origin in the xy plane. Z equals 0 plane. And above, z equals 4 minus x squared minus y squared. So let's draw our friend here. Again, give myself some axes. And let's see here. So x equals 4. 4. 4. 4. So that's the bounded below. And then nz's going to go up to 4, and curve down. So this is the region we have. It's a flat cap thing. I don't know, kind of, to me, it looks like a bishop's top on a chess piece without the curl on it. And we want to find its center of mass. So we're going to be integrating across this volume. Let me turn off my grids now. And so we need to see what we can about the balancing points. Now, in a lot of figures like this, we have, if I built this thing with rotations here, and this circle and this circular shape here are symmetric to the pole created by Z. If I drilled a hole through the origin at the Z axis, this would be centered on that. And so by inspection, we're going to state right off the bat that our center of mass for the X is 0 and our center of mass for Y is 0. We just need to find where it's balancing along the Z direction. That means we need to find the moment about the xy plane. And we're going to need to take that moment and work our way through this integral. And so let's look at our integration here. I'm going to, if I pop on the xy plane, I'm going to have a value. If I puncture in here and I puncture back out, this is going to go from z equals 0. All right, let me get my puncturing device in. All right, puncture in, puncture out. It starts at z equals 0, and it comes out at z equals 4 minus x squared minus y squared. And now if I look at what's happening within my y direction, if I look at my y's, well, y is circular And so I'm could change this to a radial and a theta. And if I look at my radial change, then I have a radius of 4, and so I'm coming in at 0 and coming out at 2, and I'm rotating all the way around from 0 to 2 pi. So I think cylindrical coordinates offer a better symmetry for this. And if I look at the rest of my moment equation, I'm going to need z times that constant density times dz but then I'm switching to cylindrical coordinates, so that's going to be r dz dr d theta. And I think that this will give us a nice balance and the ability for us to, well, I didn't mean for that particular pun. I apologize for that. Just make sure we're checking my cylindrical coordinates here. R dz d theta. I think we have a good setup here. Sorry, I was going to say make a good balance for symmetry. Is because we use the symmetry to get the x and y components. We should use the symmetry to make the integration easier. So let's do our integral. So z becomes z squared over 2. So I'm going to bring the delta 2 out. I'm going to get 0, 2 pi, 0 to 2, and then in z squared times r dr d theta, but I'm evaluating z from 0 to 4 minus x squared minus y squared. But x squared minus y squared is minus r squared. So this becomes delta divided by 2, 0 to 2 pi, 0 to 2, 4 minus r squared squared times r dr d theta. We could expand this out, or we could cheat. We could look at this as a u sub. And if that was u, right, we say u equals 4 minus r squared, then du equals minus 2r dr. And so du over negative 2 equals dr, r dr. And so we have r dr here, r dr, talking like a pirate. And so I get u squared, right? With the negative 2 in front of it. And so we'll make this negative 1/2 4 minus r squared cubed, evaluated from 0 to 2 d theta. Right, a quick u sub on it. Oh, I forgot. Forgot a 3, didn't I? Yeah, when I took u up, it would be 3, so that becomes 1/6. I got to get the 1/2 from here, and then when u goes up to 3, I need to divide by 3, so that's negative 1/6. Let's clean this up then. So I'll do my evaluation now then. That's negative 1/6. 4 minus 4, which is 0. Minus, so plus. I'll write the whole thing out. 4 minus 2 squared minus 1/6, 4 minus 0 squared, everything cubed. This is where I always mess up. There's my little maths. So delta over 2, 0 to 2 pi. And this is going to give me 0. So 1/6 times 4 cubed, which is 64/6. And 64/6 is 64/6 divide by 3. No, divide by 2. 32 thirds. Um, 4 cubed, 16, 64/6. 32 thirds. I canceled a 2 in there somewhere because 32 thirds is the number I want. Oh, yeah, cancel the 2. That becomes 16 thirds d theta. Knew I was missing a canceling of a 2 there. Yeah, 16 thirds is what I want. And so 16 delta 3, 0 to 2 pi d theta. That's 2 pi, or 32 pi delta over 3. And so we have the moment about the xy axis. And now we need to calculate the mass function. Because if we need to find the z value, we need to find the mass in the region. And dz, I'm going to put the r, dr, d theta, and we still have the 0 to 4 minus r squared in here. And we'll work out the integral here. That's going to be, you're right, it's the same boundaries of the integral. We'll change across. So we're going to get z, so 4 minus r squared and then we're going to have 0 to 2, 0 to 2 pi, r dr d theta. Right, because this becomes z, it's this minus the 0, so it's 4 minus r squared. It's not squared this time because we don't have a z in it for the moment function. So 4, this is going to become 4r minus r cubed over 3, evaluated from 0 to 2, 0 to 2 pi, d theta, and the 0 won't matter, so this will be 8 minus 8 thirds. 8 minus 8 thirds. It's missing a factor of 3. Let's see. Bum, 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 bum. Oh, and my row. Well, let's make sure I got my integral right here. So this becomes rho z, z, evaluated from 0 to 4 minus r squared. 4 minus r squared minus 0. So 4 minus r. So when I do dr, 4r minus r cubed over 3. That's going to be 8. Hold on here. Yep, I see what I did. Forgot to multiply my r through. I was rushing my integral. Do this a lot with moments because you can see what's going to cancel out with the mass function, and you want to get to it, but I want to multiply my integral, my r through. So 0 to 2 pi, 0 to 2, 4r minus r cubed, dr d theta. Now we're going to get r squared, 2r squared, right? Minus r to the 4th over 4, evaluated from 0 to 2. So that's going to be 0 to 2 pi, evaluated, let's see, 8 minus 4 d theta, right? Which will be 4 times 2 pi, or 8 pi, and I keep forgetting dizzy little delta in there. 8 pi delta. So my center of mass for Z is 32 pi delta over 3 divided by 8 pi delta, or 4/3. And so our total center of mass is 0, 0, 4/3. Sorry about the rush in there. I'll clean it up in the next videos. Notice how the choice of coordinate systems do make these go easier. Your book starts out in XYZ coordinates and switches over to cylindrical before even introducing cylindrical. I don't understand your book some days.